Hello there. My name is Dave Baxter. I'm the chair of physics here at IU, and I wanted to walk you through a demonstration lab on polarization, which is a topic you're about to study in P202. We'll walk you through a number of demonstrations that show you this phenomenon, and even though you haven't studied it in class yet to get the theory, we're going to show you some of the phenomena that are going to be explained by that theory when you get around to it. We're going to start with a simple light table here. So we have a light behind a piece of plastic projecting light upward, and we have three filters that look gray, and you see that they block a little bit of light coming through the table, but not a lot. Now, if I put two of these guys on top of each other, however, you'll notice that the amount of light that gets through the pair can be pretty much as gets through a single one if I have a particular orientation, but if I rotate it, I can get it so virtually no light gets through. I'm going to take a little pen and mark the spot where that happens. Right there, and I'm going to see, I can do that with this. So it's clear that these are filters that do more than just block half the light or some part of the light. The light that gets through depends on the orientation of the filters. The other thing I want to notice is now I've got two of these small guys that have been marked in the same orientation. If I take them away from the big guy and put them on top of each other, lined up as they were oriented before, so the red marks are together, then a fair amount of light gets through the pair. But if I, again, rotate one with respect to the other, I can get it so that almost no light gets through, certainly much less than before. And you'll notice that at that point, the two red marks are lined up roughly 90 degrees with respect to each other. So we find that there is something about light that is sensitive to the angle between these two films. We call these polarizing films, and that's one easy way to develop what is called polarized light. I want you to keep in mind that 90 degrees, and we're going to do a few quantitative measurements over the next few videos, but this is the start of the phenomenon. Okay, here we are back again where we started the light table, and I wanted to take you through a few more demonstrations now involving two big polarizers and looking at things that go on when we stick something in between, like we saw with that liquid crystal display before. So here is my second polarizer, and again I'm going to line it up so that the two are pretty much crossed so I don't get any light coming through. But as we saw with the liquid crystal, if I stick another device in between, in this case one of our small polarizers, again, as I change the orientation of it, I can get more or less light through. Oh, but now looks like it's not 90 degrees anymore. Think about that for a minute. As with the liquid crystal, it doesn't have to just be a polarizer. You could have something else in between that will cause light to pass through. Again, make sure I'm lined up perpendicular. And notice the Tygon tubing also seems to do something to the polarization of the light, because I can see light coming through where the Tygon tubing is. It has some what we call optical activity and can rotate the polarization. You'll also notice that the pattern I get when I have the Tygon in there depends on such things as how strongly the Tygon tubing is being stretched. This is a way of actually measuring stress fields in devices, and a lot of people did that with plastic in the early days for prototyping engineering materials. Now I want to be a little more quantitative, so I'm going to put a protractor in there. I hope you can read the gradations on it. And let's take another look at that first demonstration we did with the small polarizer. I put it in there oriented at 90 degrees, and I hope you can see that there's still black on either side of the protractor there. And now I'm going to be a little bit more quantitative, like I said. So I'm going to rotate this. That's about 70 degrees. I want you to look at how bright it is and try and be quantitative. There's 60 degrees, 50 degrees, roughly. 40 degrees, you can figure out what the error bar is on this. Maybe there's 30 degrees, 20 degrees, 10 degrees, and 0 degrees. Let's go back around to roughly 45 degrees. Now, you may also have noticed that that protractor looks a little bit different if it's between the polarizers than it does if it's not. And you'll also notice that what's going on in the polarizer looks a little different in near places like the holes here and the corners here. It turns out, like our crystal or calcite crystal, this is birefringent, and the birefringence, how much one polarization gets treated differently from another, also depends on the stress of the plastic and the orientation of the plastic molecules. And you see patterns show up in places where there are large stress left over from the molding of the plastic.